Okay, so here we are, final class. For how many of you is this your last class? For how many of you is this your last class at UVM? A few people. Okay, very good. Okay, we're going to do things a little bit differently today. We've got a little bit of logistics to go through. I want to just touch on a few aspects of the final project. Talk about how you calculate your final grade. Make sure we're all on the same page before we head into the final exam. I think we'll spend about a half an hour this morning just finishing off lecture 26. We'll skip around a little bit. And again, this lecture is a little bit involved, but what we're trying to take out of lecture 26 is why we might want to use an evolutionary algorithm rather than a learning algorithm. We will then spend the second half hour as just an open period, question and answers. We've covered a lot of ground in robotics and AI. We'll open up the floor to any questions or ideas you have, certain topics that we talked about that you want to come back to, aspects of robotics and AI that we didn't talk about that you'd like to bring up. Obviously, we didn't spend a lot of time talking about ethical concerns, so obviously we should spend some time talking about killer robots. Basically, just we'll have a discussion for about half an hour, which will take us to 9:30. I will then leave, and please stay for the remaining 15 minutes and fill out student evaluations if you haven't. I know it's a bit of a pain, but it does help. It does help us try and improve our courses for next year's students. Sound good? Okay, so all the way back to the syllabus. Hopefully you've been following along with the syllabus as we go. Let's see. So let's talk about quizzes for a moment. There is no quiz today, and the reason why is because you've now taken 25 quizzes. Quizzes are worth 25% of your final grade, so 1% for a quiz. You're all done with the quizzes. I'm sure you're all happy about that. Okay. Okay, 10 programming projects. That one is pretty straightforward. The final project, we'll talk about that in a moment. Participation, after you all fill out today's attendance sheet, the TA will type them all in, and then later today or tomorrow, you will see an additional item in Blackboard, which is your participation grade. As I mentioned, it's 5% if you've been here most of the time. If you missed more than 3 classes, no participation grade. So check your participation grade. If you think it's incorrect, please let me know and we can work that out now, again, before we get into next week and final projects. Okay, so by tomorrow, you should have all of your grades for this course in Blackboard except your written report and your oral presentation. So let's talk about those for a moment. As I've mentioned several times by now, obviously the grad students, you've been doing more weekly reports than the undergraduates. So the weighting for the written report and the oral presentation is different for undergrads and graduate students. You will see in Blackboard that the written report is 11 points and the oral presentation is 11 points as well, which is correct for the undergraduates. For the graduate students, you will still see that it's showing up as 11 and 11. I will be applying a weight to that to reduce it to out of 7. 7 for the oral presentation and 7 for the written report for the graduate students. So everything you see in Blackboard should tell you what your final grade is, with the exceptions of the graduate students. You need to multiply your written report and your oral presentation grade by whatever that is, 7 over 11. Make sense? Okay. All right, an important note about the oral presentation. I've created the schedule, and it turns out that you all have an additional 30 seconds for your oral presentation. So please make sure that your YouTube video is exactly 3 minutes long. Okay. As I mentioned, unfortunately, I will not be here during the oral presentation. During the oral presentations, let me bring up the schedule for a moment. Okay, so we're going to start promptly at exactly 10:30 a.m. and if everybody stays to exactly 3 minutes, we'll have 2 12-minute breaks and we will finish at exactly 1:15 p.m. I do not believe that everybody will be submitting an oral, everyone will be submitting a video, so there will be a few students here that will not be presenting. So the times that you see here are estimates. So if somebody is not here to present, we will simply move on to the next student and off we go. I will not be here. I will be watching the presentations through Skype. Jack, the TA, will be here, and Sam and Colin, my graduate students who guest lectured in this course, they will also be here to help make sure everything runs smoothly. Remember to submit your video at 11:59 p.m. next Monday, so Jack, the TA, has time to stitch all of the videos together into a playlist. If he doesn't get your video by 11:59 p.m. or if it's not set to a public setting, you can't present because we can't add it to the playlist on the day. Fair? Okay. All right, so we will write the schedule up on the blackboard here at the beginning, Tuesday morning. So when someone is presenting and you see that you are the next person to present, please come up and stand at the other side of the screen there on deck, so you're ready to go immediately when the playlist switches from the current student's presentation to your presentation. Okay, and what we're looking for in the oral presentations, that's all in the final project document. We're all good? No questions? Yes?
I think it's still scheduled to bring USBs on the final.
Thank you for that. That's the other thing. So some of you may still have USB drives. I think there's still a few out there. Please remember to bring them to class on Tuesday and drop them off with Jack, the TA. Okay. Okay. Any other questions about the final project? Okay. All right, so back to lecture 27. Why might we want to evolve robots rather than apply a learning algorithm? Evolution allows us to tinker with the body plan and the neural controller of the robot simultaneously. And we can also do this at different timescales. So in the experiment that we've been looking at in this lecture, this is a series of experiments that I ran a few years ago, we introduced an additional wrinkle to the evolutionary algorithm, which is ontogenetic change. So obviously from generation to generation in an evolutionary algorithm, the neural controllers of the robots are changing. You can also broaden the evolutionary algorithm so that it's also altering the body of the robot over evolutionary time. But we can also allow evolution to tinker with the way in which a robot's body and brain changes over a single pyrosim simulation. Why would we want to add in that additional complexity? As I mentioned, one reason we might want to do that is that it breaks the problem into bite-sized chunks for evolution to digest one after the other. The example we're looking at today is this idea of morphological scaffolding, where we're going to try and train an upright-legged robot to walk, but instead of starting with an upright-legged robot where evolution has to solve the displacement problem and the balance problem simultaneously, we're going to start with a robot that's lying flat on the ground. And over evolutionary time, and in some cases also over the lifetime of an individual robot, that robot is going to go from lying flat on the ground to standing upright. And if scaffolding is working in this case, it should allow us to eventually find a controller for the upright-legged robot to get it to walk towards the target object. That's the idea. Okay. So why allow evolution to change body as well as brain is because we want to start with, in many cases, we want to start with a simpler body where evolution can get started on the problem and then allow the body to become more challenging and allow evolution to basically track that change over evolutionary time. Okay, we ended last time by introducing a series of 5 experiments. So I'll just go through these quickly again because it takes a little while to sort of wrap your mind around these different experiments. Here's the first 2. The first one, pretty straightforward. What we usually do, start with an upright-legged robot, train neural controllers for it. The second experiment, we're going to introduce phylogenetic or evolutionary change. We're going to run one evolutionary algorithm, but we're going to pause that evolutionary algorithm 3 times, here, here, and here. And we're going to pause it whenever the current robot gets sufficiently close to the target object. So when the flat robot gets sufficiently close to the target object, we pause the evolutionary algorithm for a moment, rotate the legs 30 degrees towards the vertical, and then unpause evolution. So from evolution's point of view, it's still just evolving neural networks, but it's evolving them against a slightly changed robot. What happens to the fitness landscape when we bend the legs to 30 degrees? How does the fitness landscape change?
We don't know. It just changes. That's what we know, right?
It changes. We don't know how it changes. We do know that at this point there's a controller that's sitting on the top of a pretty tall hill. That's the controller that got the flat robot to the target object. But probably when we change the body, that hill is going to decrease in height by some amount. We don't necessarily know how much. And perhaps somewhere nearby, another hill has increased in height, and evolution is able to produce a child, then a grandchild, then a great-grandchild, and gradually move from that lowered hill to a new higher hill, which contains at its top a controller that gets the 30-degree robot to the target object. Pause, alter the robot again, which alters the fitness landscape, and on we go. Right? We can then ask the question, as you can see in both experiments, we end up with the upright-legged robot. How many generations did we have to run? How much computation did it take to find a controller to get the upright-legged robot to the target object? That's what we'll see in a moment when we get to the results.
On the graph for this, even though we're pausing the evolution when it got a third of the way to but for the next generation, it's back again. Right? We give the controller, we set it back to 0 and it tests it.
The controller doesn't necessarily go back to 0, right? We have a controller.
Position 0.
Position 0, right. The robots are always, as always, starting at the origin and trying to move towards the target object.
The parent got far.
The parent got far with the parent body plan. When we change the body plan, who knows? Maybe it'll get half as far, a third as far, hard to say, right?
So throughout the scaffolding, they have different fitness functions?
It's the same fitness function. The distance to the target object. Okay. We're trying to minimize distance to the target object. Fitness function never changes. The body of the robot changes, which changes the fitness landscape, right? It's a little bit different from what we've seen before. Usually we have an evolutionary algorithm, we change the fitness function, and that obviously changes the fitness landscape.
So just distance to the box, it develops balance to help it accomplish that task.
Absolutely. So the task is simply get as close to the target object as possible. So it's like phototaxis, except we're not doing 4 environments, we're just doing 1 in this case. Okay, so that's 2 experiments. Let's look at a third variant on this. In this case, the robot's body is still changing. So let's look at phase 1 here. We start with the robot lying flat, and now over the robot's lifetime, during one pyrosim simulation, the legs are going to become increasingly vertical, which means the center of mass, the height of the center of mass of the robot is gradually increasing over that one pyrosim simulation, right? So this is meant to be sort of a very rough analog of our own ontogenetic trajectory, our own developmental trajectory, where we all started lying flat on the ground and gradually over the first part of our lifetime figured out how to maintain upright stance and balance while moving from point A to point B. Unlike us, however, this ontogenetic change itself changes over evolutionary time. Once the flat to upright robot evolves a controller that gets it to the target object, we pause evolution again, and now change the ontogenetic trajectory. So now the robot goes from flat to upright over the first 2/3 of the pyrosim simulation. So we made a slight change and then has to maintain the upright-legged posture for the remaining third of the pyrosim simulation. We're accelerating the flat to upright transition. In the third phase, we accelerated it again. So now the robot's going from flat to upright over the first third of its lifetime and maintaining an upright stance for the remaining 2/3. And then in the final phase, as always, the robot starts in the upright stance and has to maintain the upright stance throughout. So this is not unlike a lot of mammalian species that are prey, that are born and have to start running immediately after birth for obvious reasons, right? Unlike us. Okay, so we have phylogenetic change. The robot's bodies are changing over evolutionary time. And we have ontogenetic change, going from flat to upright. That's experiment number 3. So far, so good?
So on the x-axis, there are multiple runs of the simulation, like 1, 2, or this.
So this big axis here, phylogenetic time, this is all one evolutionary run. We don't know how many generations. We're basically going to just keep running it until this one evolutionary algorithm gets through all 4 phases. When does it switch from one phase to the next? When evolution finds a controller that gets the robot sufficiently close to the target object. We set some threshold within 1 meter of the target. So in some runs, it takes longer to get through, it takes more generations to get through phase 1 than it does when we reset and start with a different random population and run it again. Depends on our starting material. So far, so good? Okay. Experiment number 4, we're going to introduce yet another wrinkle, which is this idea of topological change. So I'm going to use parametric change and topological change. Parametric change is the parameter that describes the angle of the legs relative to the main body. Topology here is a reminder that in this set of experiments, the actual number of body parts is going to change. We're going to start now with a legless robot, and it is gradually going to grow legs over evolutionary time. I showed you a video of this last time. Maybe it's worthwhile just watching this again. And we spent a little bit of time last time talking about how you can actually do this in PyroSim. But anyways, we have a legless robot that gradually grows legs. In this 4th experiment, there's no ontogenetic change. A legless robot is born legless and stays legless throughout the PyroSim simulation. But there is phylogenetic or evolutionary change. Over many generations, over this evolutionary algorithm, legless robots are gradually replaced by robots with short legs, then longer legs, and then finally long upright legs. You'll notice in all 4 experiments, we're always ending in the same place. The goal here is we want a neural controller for the upright-legged robot. And we're trying different kinds of scaffolds to see which, if any of these scaffolds, helps. Okay, last experiment. We're going to put all these 3 things together. We're going to have phylogenetic change. The robot's body is changing over evolutionary time. We have ontogenetic change. The robot in phase 1 is going to be born as a legless robot, and as it's moving, as you just saw in the video, it's going to gradually grow legs that become increasingly vertical. And it's this topological change. We're not just varying a parameter, which is the angle of the legs. We're going to start with a different topology, a snake robot, and it's going to change into a new topology, which is the legged robot. So we have 5 different experiments. We're going to do multiple trials, multiple runs of each of these 5 experiments, and ask the question, on average, how many generations does it take to find a controller that gets the final upright robot to the target object? Okay. Which one wins? Which of these evolutionary algorithms is easier for evolution to eventually find a controller for the upright-legged robot? You can guess by the fact that we're talking about this. It's not the first one.
The combination.
Yes, and again, you can probably tell from the ordering it's going to be this one, and we'll see why in a moment. Okay, so let's start by let's look at some results, and we'll do this gradually. So we're going to look at this light gray bar here. This light gray bar corresponds to experiment 1, no scaffolding. In this set of experiments, we placed the target object about 5 meters directly in front of the robot. Run evolution, and instead of recording the number of generations, which gets a little confusing, we're just going to use the number of simulations that evolution had to run through, the number of evaluations. So it took on average about 5,000 evaluations to finally find a controller, to finally evolve a controller that got this robot within 1 meter of the target object. Okay, that's our starting point. We then look at experiment number 2, and it actually took a little bit longer to find successful controllers for the upright-legged robot. So this particular scaffold is not helping us. It's actually making things a little bit worse. Third experiment, phylogenetic and ontogenetic change, also is making things worse, not better. So this is one of the tricky things about scaffolding. If you think about putting training wheels on a bicycle and having a young person learn how to ride, they're not really riding a bicycle. They're riding something that is kind of like a bicycle and also kind of not. The moment you remove the training wheels, the experience of the learner changes slightly. Suddenly, this machine is responding slightly differently than how it did before. So the learner has to adapt a little bit to how they're controlling the machine to get it to work. Not unlike these evolving neural networks. They're trying to control this robot body, but the robot body is changing over the evolutionary process. That can often make things worse, not better. Okay, so we got a little nervous at this point. Didn't seem to be going according to plan. So we started to change things a little bit. We did 100 evolutionary runs of the first experiment with the block directly in front of the robot, 200 evolutionary runs of this experiment, 100 evolutionary runs of this experiment. Then we did another set of 300 trials, 300 runs, where now the target object was placed pi over 16 radians to the robot's front left. Still didn't seem to make much difference. 2 pi over 16, 3 pi over 16, and finally, when we put the target object front left of the robot, now the scaffolds seemed to be helping. If you look at the light gray bars, they're increasing in height, which means by moving the block further and further to the left, it makes it harder for evolution to find a controller for the upright-legged robot to get it to the target object. Let's just think about the light gray bars for a moment. Why? Why is placing the block front left making things more difficult than placing the object directly in front of the robot?
How does the robot sense? Does the robot just have a light sensor in the center?
Exactly the same as assignment 10.
Does it have to change its behavior in its legs?
It has to change its behavior. How?
Find the light source first and then go to it.
Maybe. We're not doing phototaxis here. We're only placing the light source once. So it may or may not be using the photo sensor. It could actually just be using touch information. But regardless of whether it's paying attention to the light sensor or not, what does the robot need to do when the object is front left?
It has to change the way it moves its legs, because before the light source was in front of it, so it evolved a certain way, I guess, of moving its legs, and then when the light source is to the side,
It has to change. You're close. Maybe I misspoke here. So we're actually looking at a whole bunch of completely independent evolutionary runs. We did 100 evolutionary runs here, 100 here, 100 here, which gives us a total of 300 evolutionary runs. And at the end of each of those runs, we stop. We're not borrowing something into the next. We're not bringing something into the next run. So we did 300 evolutionary runs here, another 300 here to give us 600 runs in total. 600, 900 runs, 1,200 runs, 1,500 evolutionary runs. So in this set of 300 runs, the robot only ever sees the target front left, which apparently is making things harder for evolution. Why?
I think that if you start the robot off with the legs straight and learn to walk kind of like this.
Yep.
Because they can't turn. But if they're sideways, it has to kind of sidle, and that allows for turning.
Absolutely. So when the object is front left, the robot has to turn somehow, right? And if it's turning, the chance of falling over is actually greater. As you're moving and turning, there is centripetal force that's pulling you to the right, and you're much more likely to tip over. So in this case, where there is no scaffolding, evolution has to solve the displacement and balance problem, and the balance problem is even harder in this case than it is in this case. So the light gray bars, evolution is trying to solve both problems at once, and one of those two problems is getting harder. Right? If you look at the gray and the black bars, they're also increasing, so things are still getting more difficult, but they're not increasing at the same rate, so the scaffold is becoming more useful, which kind of makes sense because the scaffold is breaking this problem into two pieces. Get the robot to move first, move towards the block, and then when you're figuring that out, now gradually alter the neural network as the robot starts to stand up. Keep moving towards the block, but focus on not falling over as you become increasingly unstable. Question?
When in the one with no changes that did poorly in the 4 pi over 16.
This one, yep, the light gray bar.
Did you see behavior where the robot was turning toward the object while it was moving, or was it kind of skittering diagonally?
All of the above, right? So in all cases, it's either turning and walking towards it, or it's bending its body and trying to move. All of these things tend to make it more difficult to keep upright balance than it is to just move forward towards the block. Okay, so things are looking promising here, but we've only looked at the first 3 experiments. Let's look at experiment 4 and experiment 5, which is this idea of topological change. So in 4 and 5, we're starting with a legless robot that's growing legs over evolutionary time. So let's look at this panel here. So you can see this panel looks very much like this panel. The light gray bars here are exactly the same, or they're reporting the same experiments as in this bar. It's the no scaffolding case. We did 100 runs of this experiment, which is the gray bar here, and we did 100 evolutionary runs of the 5th experiment, which is the black bar in this panel. And vertical axis, again, is telling us on average how many simulations had to be run until evolution found a controller that got the upright-legged robot to the target.
I'm a bit confused.
Sure.
What indicates the placement of light source, like in the directly in front in these figures?
Yeah, sorry, let's go back here. It's a little bit easier to see. So these 5 groupings of the bars represent different environments. So in this one that says 0, that means the target object is directly in front of the robot. In this set of 300 runs, the target object was placed pi over 16 radians to the front left of the robot. So 5 different groupings of bars, 5 different environments. Okay. Let's talk about experiment 4 for a moment, which is the dark gray bars in this panel. These did much worse. Experiment 4 was the worst out of all of these. Why? Why did evolution find it so difficult to evolve controllers along these 4 bodies until eventually finding a controller that got the upright-legged robot to move?
It's a sharp return.
Not quite a sharp return. They all have the same environment, right? So over here we've got 4 pi over 16, so the object is still front left. Why is this so difficult?
Just a very large body change, and you go from no legs to having to stumble about. It's quite a different controller.
Absolutely. So think about the controllers that are being evolved for this robot. It's basically a snake robot. The only thing it has is its spine to move it, which it can do. It can get to the target object. We pause evolution, and then when we restart evolution again, suddenly there are these 4 new body parts that were never there before. There are these 4 motor neurons, which up until this point have basically had no effect on the body. They're just empty. And suddenly they're affecting the sensor motor coordination, right? I'm trying to think of a metaphor with the training wheels here. You have somebody who's riding a bike with 2 wheels, and then suddenly there's 4 wheels in series. It's not a bicycle anymore, it's completely different. So whatever experience these neural networks have accumulated, they're useless on this robot. If we have a controller that's getting this snake robot to move, it's a controller that's sitting on the top of a hill in a fitness landscape. And the moment we add on those 4 legs, that hill drops all the way back down to the ground. That controller that worked for the snake probably does nothing for this quadruped that has these very short legs. It's got to basically start over from scratch, right? Okay. Experiment 5, however, which also has a robot that starts legless and grows legs, has the opposite. It's very useful. So if we just look at this grouping here, in this case with no scaffolding, it took about 15,000 simulations to find a controller for the robot that worked, and about 2/3, about 10,000 evaluations for experiment number 5. Why was experiment 5 so much better and experiment 4 was so much worse? They look kind of similar, those 2 experiments on the surface, but had very different results.
From the very first generation, it gets legs before it's done with its life, so it's got some clue as to what to do with them.
Absolutely, right? So the controllers that work here, these controllers have had experience with the legless robot during the first 100 or so time steps of a pyrosim simulation. And they continue to control the robot as those legs are getting longer and more vertical. So we're training controllers here that are able to successfully move different robots to the light source. Still the same robot, but it's going through different phases. Right? It's kind of interesting. If you think about your own spinal column and your own control of your own bipedal movement, your spinal column has experience controlling your body and trying to get you from point A to point B when your body looked very differently from one year to the next, right? Your nervous system can not only control your current adult body, but has experience with your body in very different forms. That's very similar to the evolved neural networks here. In this experiment, when we pause evolution and then change the developmental trajectory and unpause it, these evolved neural networks are not as surprised as they were in experiment 4, right? They're still controlling initially legless robots that grow legs over one pyrosim simulation. They're just growing those legs a little bit faster. That's all. Right? Okay. So you'll notice the little asterisks up here. This is just a notation to us that the difference between the black bar and the light gray bar here, this difference is statistically significant. It's real. Some of these other differences are kind of small. They might just have been due to chance. But we definitely know that experiment 5 is helping when we're dealing with the light source placed front left. To confirm that, we did all these experiments with the quadruped that you saw in the video. We redid everything with the hexapod. So we redid all 5 experiments with the hexapod and got more or less the same result, although in this case it was even more helpful than compared to the quadruped. So at least for 2 different robots, we can see that morphological scaffolding helps. Bodies that change can make things easier on evolution. It's trying to produce neural controllers for the robot. But the way in which those bodies change matters. We can't just evolve on a snake and then suddenly try and transfer those controllers to a quadruped. We have to do things gradually, which is, of course, exactly what happens in nature. In nature, our bodies and our nervous systems change gradually over our lifetime and also over the lifetime of our species. Changes to genetic code don't change a trait. They change the way that a trait is expressed over the lifetime of an individual. Okay, so evolutionary robotics is often shortened to Evo-Robo. Now we have Evo-Devo-Robo, right? We have the development in there. And Sam, who works on soft robots that was here before, likes to talk about his work as Evo-Devo-So-Ro. So for the soft. So there you go. Okay. All right, last set of results, and then we'll switch to a discussion. Last plot I want to show you is this one. I'm going to switch back and forth between these a fair bit. We've got 300 experiments, 300 runs, 600, 900, 1,200, 1,500 evolutionary runs, 1,800, 21, 24, 27, 3,000 evolutionary runs at this point, 6,000 evolutionary runs. This took us a very long time on UVM supercomputer. We have 3,000 evolutionary runs. At the end of each of these 3,000 evolutionary runs, we have one controller that got the upright-legged robot to the target object. We extract the best robot from each of those 3,000 runs, which gives us 300 highly fit controllers. We then reran those 3,000 evolved controllers back on the upright-legged robot. But now, as that upright-legged robot was moving, we added wind to the simulation. We added random external perturbations and asked the question, how robust were those controllers? During evolution, as in PyroSim, as always, the robot is moving through a vacuum. There's no air resistance, there's no wind. What happens when you expose these controllers to perturbations they never saw during evolution? We've seen that in a few experiments throughout this course. That's what this second plot shows us. So now the height of a bar, let's take this bar here, the height of this bar reports the percent drop in performance of these evolved controllers in the windy conditions. You notice that this is hovering somewhere around 23%. This means that however far those evolved controllers moved in vacuum, they moved 87% as far in the windy condition. They were slowed down by 23% when exposed to wind. You'll notice at the end here, the black bars tend to be lower than the light gray bars, which tells us what? What can you tell me about the evolved controllers from experiment 5 here compared to experiment 1?
Experiment 5 is more robust to perturbation.
The evolved controllers from experiment 5 were more robust. There was less of a drop in performance when they experienced wind than the evolved controllers with no scaffolding. So I'm going to flip back and forth between these slides. I want you to pay attention to the evolved controllers from experiment 1 and experiment 5, just in this grouping for a moment. It took us less time to evolve these controllers, and they're more robust. When we got this result about robustness, we were extremely surprised because everything you've seen in this course up till this point says if you want to have a robot that's robust, you need to do more simulations. If you want to evolve a robot that's robust to where a light source is placed, like in assignment 10, you got to evaluate every controller 4 times, not just 1 time. And even then, maybe it didn't work so well, right? So if you want controllers for robots that are robust, you tend to have to evaluate those controllers more times. This is the only exception I know of to this rule. How is this possible? Why are these controllers more robust and we obtain them in a shorter amount of time?
You happened to get lucky and started on the slope of a much higher point in the fitness landscape.
We could have gotten lucky, but if you look at a bunch of these other groupings, you'll notice that usually the black bar is lower than the light gray bar in most cases. So we didn't get lucky. There's definitely something going on here. What's going on?
I don't really know how to put it into like robotics terms, but like better fundamentals of like how to walk.
Better fundamentals of how to walk, that's right. Can we be a little more specific?
Since the light source is already placed far to the right or left, they're already in worse conditions, so they're being trained in the worst conditions, so.
Maybe. So it's obviously it's harder to approach the block that's front left than straight in front.
The controller in that evolutionary run already experiences some change with its legs.
That's it, exactly, right? The controllers that we're pulling out of these runs at the end of evolution, they've already experienced change. They haven't experienced change from vacuum to wind. That they never saw that change during evolution. They only saw it when evolution was over. What change did they see during evolution?
Their legs.
Their legs, their internal body. Their internal bodies were changing, not the external world. And it turns out that at least for this set of experiments, it's probably not a general principle, but at least it's possible that the changes the robot experience in its own body makes it robust to changes in its environment. Kind of interesting, right? Again, we also have experienced massive changes in trying to put one foot in front of the other without falling over in very different bodies, which maybe makes us a little bit robust to exhibiting locomotion in lots of different environments that maybe we didn't experience when we were young children. Maybe it makes us robust in other ways. So we are a species that exhibits quite a bit of morphological change. Our bodies change greatly over our lifetimes. Not all organisms experience as much morphological change as we do. We also tend to be one of the most adaptive species around. We seem to be able to deal with very different environments. Is there a relationship between these two things? Maybe yes, maybe no. Okay, I think I'll leave things there. I just want to show one final slide before we have our discussion. And as you can see, this slide has absolutely nothing to do with robotics. This is taken from a book, an economics textbook, and obviously you can see the data is a little out of date now. It only runs from 1963 to 2008. What it is plotting is it's plotting some economic data for full-time employed male US workers. In 1963, they took all the data and normalized it to produce this vertical axis here, which is weekly wages. So basically, how much did you get paid based on how much schooling you had? They normalized it to 0, so everything is about the same. And then moving forward, they asked the question, moving on from 1963, how did someone in 1964, for example, get paid for the same level of education compared to someone from the year before? So far, so good? Let's have a look at the blue curve, the high school dropouts. How were high school dropouts doing in 2008 compared to high school dropouts in 1963? Doing worse. So again, controlling for inflation and everything else, they were at more of a financial disadvantage in 2008 than their compatriots were in 1963. The fact that you're all here means you are not high school dropouts, so let's move on. High school graduates, how are they doing compared to 1963? About the same. Some college, maybe. College graduate. Anybody want to guess how this curve has progressed from 2008 to 2019? It's not quite as high as it was in 2008. The only winners in this cohort are those that go to graduate school. So the final message that I have for you in this course, stay in school. Okay. Hopefully we will see some of you coming back for a master's or maybe a PhD. Okay. Let's switch now. I apologize, it's not as much time as I'd hoped, but let's spend about 15 minutes sort of opening the floor to any topic you'd like to talk about. We've covered a lot of ground in this class. Anything you'd like to discuss?
I have two pretty general questions.
Sure.
I know that Nick Cheney studied evolutionary biology, I think.
Yes.
But most of the other master's students that spoke have studied basically this, I guess, and AI and deep learning and things like that.
Yes.
Are there other adjacent fields that study kind of the same thing in master's degrees and PhDs?
That's a great question. So the question is about formal training. So as you mentioned, Nick, who is here, has a more interdisciplinary background. One of his graduate degrees is in biology. My graduate students that are here have more or less progressed through computer science and math. Obviously, biology is an adjacent field. Cognitive science is sort of a subset of philosophy. As you can see, there's a lot of overlap between what we've talked about and cognitive science. So cognitive science, unlike neuroscience and psychology, try to dissociate a little bit from the details of the human nervous system, right? Can we ask questions in cognitive science about cognition in general, right? What does cognition have to look like to work for animals, humans, machines? That's a very closely related course. A good way to do that is to basically just Google graduate schools and put in pairs of keywords for pairs of fields: computer science, cog-sci, computer science, evolutionary biology. Those are pretty related. Yeah, absolutely.
And then my other question is, almost everybody who came in talked about like soft body robotics.
Okay.
It kind of seems to be, and you just mentioned it also, like the future of the application of this. Do you think that, I guess, like, how big is there a future in that, and is there something else that's kind of like rising to either like take over that idea, or I don't know exactly.
I understand what you're saying. So obviously you saw a fair bit of soft robotics in this course. It is definitely the most hot topic in robotics at the moment. Part of the reason for that is a revolution, not so much in robotics, but in materials science. So it's getting easier to either 3D print or otherwise manufacture materials that have an arbitrary combination of soft and hard materials. There are 3D printers that are now getting better at printing plastics, ceramics, soft materials. So now that you can do that, obviously, what do you create, right? So a lot of the engineering problems in soft robotics have been solved. We can if you can simulate it, we can make it, but then the question still remains, what should be made? Where do you place soft material? Where do you place rigid material? Do you have a modular design where you have a rigid motor, rigid electronics, and a rigid battery surrounded by a soft skin? Or do you have something a little bit more exotic where there's a little bit of battery over here and a little bit of motor over here, stiffer and softer, sort of, it's more of a continuum? Nobody really knows. And as you can imagine, designing those kinds of robots is even more unintuitive than it is trying to design a controller for something that has hinges and rigid bars and arms and legs. So a lot of interest in soft robotics. What's going to come after soft robotics? Again, nobody knows. Sam, who is here, talked briefly about simulating soft robots and then making them out of biological cells. I think that's definitely the next frontier. Why do we need to build soft robots out of purely artificial materials? Can we combine biological and artificial materials together?
So the paper that you participated in with like numerous other professors and that you guys released last week for calling for a new field called machine behavior.
Yes.
So why have you determined that we need a new field, machine behavior, and do you hope to, out of that call for a new field, get like a theoretical look at some of these, or get some generalized rules to come out of this? Or?
So that's a great question. So last week we published this paper calling for a new field of machine behavior. Many authors on that: computer scientists, engineers, philosophers, ethicists, legal scholars. Hopefully, as you've seen in this course, there are a lot of issues in robotics and AI that are difficult for just a computer scientist or just a mathematician or just a biologist to tackle. A lot of the most interesting questions that are arising in AI and robotics are interdisciplinary. They lie at the interface. So the reason we called for this new field is that we need to bring these people together and ask questions at the interface. We can bring a whole bunch of people together from different disciplines and they all still do their own thing and everyone's sort of playing their own game. How do we get everyone to speak the same language? In that paper, we had one figure that laid out what's known as Tinbergen's 4 questions. I can't remember now if we've actually talked about Tinbergen in this class. Tinbergen was a scholar of animal behavior who pointed out that you can look at behavior from lots of different directions. For legged locomotion, you can ask about the musculoskeletal system that gives rise to walking. You can ask about development. How does legged locomotion arise in humans over their lifetime? You can ask about the evolutionary pressures that selected for bipedal locomotion among our ancestors on the African savanna. They're all valid questions about behavior. If we want to try and analyze machine behavior, we need to approach it in the same way. Not just ask about an autonomous car, about why it made a decision at that point in time, at that intersection. What was the data set that it was trained on? Who produced that data set? What was the version of the code before that trained autonomous car software before? We need to look at the big picture and come at it from all angles to be able to conclude with certainty about how a machine will behave under certain circumstances. Another question.
Do you think it's possible to create like really adaptive robots by having the simulating power within the robot? So we talked about being able to evolve simulators, like evolve accurate representations of the environment. So by comparing the difference between physical movement and what it thinks it would do.
Sure.
So if we put that computational power within the robot itself, do you think we could make more adaptive real-time robots that could and how quickly could that process potentially take place?
Sure. So if we were able to put the simulator inside the robot and it could test things in real time in the simulation before trying them out in reality, I think that will get us part of the way.
Is it too slow though to happen
It's not too slow. It's obviously fast if it has the simulator right there, but it's only able to draw on its own experience.
Yeah.
So there's a related field in robotics which we haven't talked about in this class, the emerging field of cloud robotics. You can probably figure out what this means. You have all machines uploading all of their sensor motor data to the cloud, and you have a simulator, some model back in the cloud that is combining and digesting data coming back from all the machines. That is something that humans are only now figuring out. We have an internet. We try and put all of our common experiences up there where all of us can then simultaneously access it. Can we do the same for robots? And obviously we can probably do this with robots faster and at scale. So we might have a machine with a local simulator, but that local simulator is being trained not just on the experiences of a single robot, but all robots connected to the cloud. I think this is the way we're going to solve real-time adaptive machines.
So going back to the problem of the why don't we have robots in building and construction environments?
Sure. Yep.
It would still need to figure out what its present environment is. But then we saw the other experiment where they had a database of different controllers to pull from in different experiences. So
Absolutely.
you could find what you need and then pull a good controller.
Absolutely. So if we have a single robot operating on a construction site, it better be pretty sure about the environment before it starts acting.
Yeah.
But we may not have to assume that robot is the only robot observing that environment, right? In the age of the Internet of Things, there may be lots of other machines or devices on the construction site that are supplying data up to the cloud in real time or directly to the machine itself. So most of what we've seen in this class assumes sort of one robot operating on its own, but of course we're moving to a much more networked view of embodied machines. They're talking to each other in real time and sharing experiences through the cloud.
And also unrelated, do you know anything more about evolutionary art or any progress that's been made for building fitness functions for that?
I'm not an expert in the field of evolutionary art, but again, if you Google evolutionary art, genetic programming, and art, there's a lot of interesting projects out there to have a look at.
Throughout the course, we've been changing a lot of things other than mutation. We did not try any other way to evolve.
Yep.
And that did not read any, so why is that so, or is there something out there that we're not studying in the course?
Yeah, absolutely. So that was intentional. So we didn't spend a lot of time talking about the nitty-gritty details of different evolutionary algorithms and different ways of doing mutation. We talked a little bit about crossover when we discussed the NEAT algorithm. The reason why is there's a sister course to this course, which is Professor Epstein's Evolutionary Computation course. If you found the evolutionary algorithms in this course interesting and you have room in your schedule next year, Maggie's course is a great one to consider. It's offered at the 300 level, but I think if you speak with Maggie, you probably get some, you can probably talk her into letting you into the class. There she goes into a lot more details about the pros and cons of different evolutionary algorithms. Yes?
Do you think we'll ever be able to create a simulation where we eventually close the reality gap or get close, or will that always be like the biggest hurdle?
That's a great question. Will we ever close the reality gap once and for all? Probably not, right? It'll always be approaching, right? Evolution is not an optimizer, it's a satisficer. As we saw when we talked about the evil starfish experiment, that simulator was pretty poor. It wasn't a perfect reflection of the robot's own body, but it was good enough. So I think the more interesting question from a practical point of view is, how good is good enough to cross the reality gap? And again, it's probably not going to be perfect for all different machines, but with enough data flowing in through an Internet of Things, there should be more than enough data to create a good enough simulation for most machines under most circumstances.
So throughout the semester, you mentioned like open questions.
Sure.
So I wanted to ask, in your lab specifically, what are like the driving open questions for your research currently? And also, what do you think for this decade, for this coming decade, what are the biggest open questions that you think will be answered in this next 10 years and then for our lifetime?
Oh boy, okay. So in our lab, we're currently tackling big problems in other branches of AI and machine learning that can be helped by embodiment. One of the big open problems in AI in general is catastrophic forgetting. I think we mentioned this before. Regardless of whether you're dealing with a robot or a disembodied neural network, if you train it to do task A and then challenge it and you then train it on task B, it usually gets better at B at the same rate that it forgets A. It's very hard to get a neural network to hold on to one task, the ability to perform one task and add a new one. One of the things that's most interesting in our group, from my point of view at the moment, is if you do this from an embodied perspective, there are ways you can do this where with the right body, it's harder for the robot to forget. So you can approach the catastrophic forgetting problem through the lens of embodiment, which is often what we do in my lab. We take problems in the disembodied side of AI and ask whether embodiment can help with those problems. What's the big question over the next 10 years? That's a good question. I think the question of perverse instantiation is very important. This relates to the ethics of AI. If an autonomous car works 99% of the time, what about the remaining 1%? What is it going to do in that remaining 1%? In the course of the assignments in your final project, you probably now experience perverse instantiation firsthand. You formulate a fitness function, you're absolutely sure what evolution is going to give you back, and it gives you back absolutely not what you were expecting. You were surprised, which in this class is fine, it's entertaining. You do not want to be surprised by a physical machine in which people's lives hang in the balance. This is an open problem, and in my opinion, no one has a good answer to that. We cannot, or we're not able at this point to guarantee that the machine will stay within certain bounds of rational behavior. When a machine surprises us, we cannot guarantee how surprising that behavior is going to be. That is not just an interesting problem intellectually, but a real practical problem which is holding up the widespread deployment of autonomous machines, for sure. Maybe one more topic before we move on to student evaluations.
How can we be sure that fitness functions are continuous? And I feel like there would be a bunch of optimal that lies within like non-continuous segments of it. So where we have like sudden like vertical and then like an infinitely small point that would like produce good results, but then there's no way to get there from like a smooth. So
Absolutely. The needle in the haystack problem, right? The vast majority of solutions are very poor, and there's a vanishingly small subset of solutions that work. Again, this is an open problem. There's no way to guarantee a priori that your fitness function or your environment or your robot is not going to experience that situation.
That's why you said it's a satisfier, not an optimizer.
Exactly. We can never guarantee, we don't know how to guarantee at the moment that an evolutionary algorithm will find the global optimum, only that it finds a good enough local optimum. Okay, thank you again for your attention. It's been my pleasure to act as your tour guide through the field of evolutionary robotics. I will see you online next Tuesday at 10:30 a.m. Please stay back and fill out a student evaluation. It's very helpful to us. The attendance sheet is floating around somewhere. Please make sure to sign it before you leave. And actually, please come up and sign it now before you do the evaluations if you missed it, because I'm going to exit stage left. Okay, thanks very much, everybody. Good luck with your exams.